Welcome to a lesson with Dr. Powell. Let's take a look at an optimization problem in figuring out where a surface has a maximum or a minimum. So let's look at an example here. Negative 10x squared plus 16xy minus 10y squared minus 52x plus 56y minus 78. Okay, so let's take the derivative because we want to find a point where this function is the surface is basically instantaneously zero or not kind of flat. And so we take the first derivative f(x,y) and we want to know at what points this derivative is zero, which will give us a zero rise instantaneously for any run. So it'll be basically instantaneously flat. Okay, so we find fx and we set it equal to 0. So fx is negative 20x plus 16y, and that's to 0, and then minus 52. Okay, and we want that to be 0. Okay, then we have fy, and that's going to be 16x and minus 20y and plus 56, and we set that equal to 0. Okay, all right, so we have these two equations set equal to 0. Let's divide, we can divide by 4. Let's divide top and bottom, both of these equations by 4. So we're left with negative 5x plus 4y minus 13 is equal to 0. And then we get 4x minus 5y. Minus 5y, and then plus 14 is equal to 0. Okay, so we just divided top and bottom by 4. Now, looking at this, you can add or subtract equations to get rid of a variable if you want, if you multiply first by something. What if I multiply this top equation? Maybe I should have just kept it multiplied by 4. That's okay. And this bottom one by 5. All right, and see kind of what happens with that. Because then I'm noticed when I do that, the x's will cancel when I add the equations. Over here, I'll have 16 minus 25, which will be minus 9y. So 16 minus 25. Okay, minus 9y, and then I have so it's basically minus 52 plus let's see, was that 70, right? Okay, so 5 times that is 70, and you have minus 52, so you would get, what is that, 18? 18, okay, is equal to 0. So it looks like y is going to be equal to just positive 2. Okay, so y is equal to positive 2. Now, when y is equal to positive 2, I can throw that in either one of these equations and see what results. I'll put in this one. Y is 2. That'll be 56 minus 40, which will be positive 16. So it looks like x will have to be negative 1. Looking at that. Yeah, so negative, right. Okay, so that's good. So, and that's the only critical point that I'm getting here. So I have x is negative 1 and y is 2. That's the critical point. And now I got to check. So maybe we have a maximum or a minimum of this function at this point. Let's see whether it's a maximum or minimum. So we got to take the second derivative. So take the second derivative. We're going to take this first derivative, which is right here, written as a column. Okay, derivative with respect to x first, it's just those coefficients, negative 20 and 16. With respect to y, it's just the 16 and the negative 20. Okay, now for sake of ease, why don't we just factor out a 4 out of the whole matrix here? So we get 4 times, and that's just, what, negative 5, and 4, and 4. Okay, so all right, this is fine. We're just going to work with this. So the second derivative, oh, this is a constant multiple of the second derivative right here, and that's fine because if this acts like certain scalars, then well, you have a scalar multiple of this matrix that's positive. I mean, we're well on our way. So if we have positive scalars here, I would have positive scalars after that and negative and so forth. So really this is okay. If you can factor out by a positive number, you're okay just to use this guy. Okay, so let's just look at this one. And so what we're going to do is we're just going to make this whole matrix negative and just pop x's right in front of those guys right here, in the forward diagonal. So we're going to have x plus 5, x plus 5, -4, -4. So what does that do? That's the same thing as just saying, yeah, basically saying this matrix minus that one. Same thing as just making all those entries negative and just adding x to the diagonal like that. Okay, so then from this, we just take the determinant, which is, and the determinant is, let's just give me some room to write here. All right. So the determinant is x plus 5 quantity squared and minus -4 times -4, so just minus 16. So we get x squared plus, yeah, 10x plus 25 minus 16, which should be plus 9. So we get x squared plus 10x plus 9. And if we were to factor that, we already know about that result. We already wrote it over there. Okay, if we were to factor this, then we would notice that we would have x plus 1 and x plus 9. Now look at that. Both of these guys right here are positive, or are, well, these are positive in here, but actually the roots though are set that's equal to 0. It's actually x equals -1 and x equals -9. Those are the two roots of this equation, and both of these are negative. What does that mean? Well, that means like if we move a little bit in this direction, then actually we're going in the reverse, the gradient or the derivative is in the reverse, which means the rise is in the reverse. So we're kind of rising to that point. So that point is a maximum. So if you get negative, that's kind of like negative, like concave down, if you will, or negative concavity. So you get max, same idea. So you get negatives here in these roots, then you have a maximum. So this point right here will yield a maximum of that function. We have a maximum located at that point. Now to find the actual maximum value of that function, of course, you need to plug this in into the function right here, and you'd see what the maximum height is locally, at least around that point. Thanks for watching.